This is what we did in the last class, chapter 4. In chapter 4, we started talking about node voltage method. Okay, today we are going to look at mesh current method. Okay, node voltage method, mesh current method. Before that, I gave you a set of tools, right? The passive sign convention, Kirchhoff's current law, Kirchhoff's voltage law, series and parallel simplification. And then we went on to current and voltage division, looking at MATLAB code, then node voltage method. So node voltage method and mesh current method, both these, let's see, both the node voltage and the mesh current method are all about setting up equations. If there are n unknowns, you use KVL or KCL. Okay, when you're using node voltage method, you use KCL. Okay, when you're using mesh current method, we will see in today's class that you'll be using Kirchhoff's voltage law. To set up equations, if there are n unknowns, that would require you to set up n equations. Then it's a matter of solving them using MATLAB, a set of linear system of simultaneous equations. Okay, so let me quickly review the node voltage method, especially the steps that are involved. Okay, the steps that are involved in node voltage method are: you begin by selecting a reference node or a ground node. Then you identify the different nodes. What are all the different nodes here? And then associated to each node, you mark a node voltage. Okay, a node voltage associated with each node. Then you set up KCL at each node. Okay, KCL at each node gives you one equation. There are two nodes, gives you two equations. There are three nodes, gives you two equations actually. One of the nodes being ground. From the two non-ground, non-reference nodes, you have two KCL equations. Once you set up those KCL equations and take into account any dependent current sources, you have enough equations to solve together. Okay, that's the idea of KVL. In today's class, I'm going to talk about KCL. That's the idea of node voltage method. Now we are going to talk about mesh current method. Okay, let me go up there. We also looked at node voltage method with dependent sources. The process is still the same, except that you have to set up a third equation called the constraint equation. Okay, and we did an example. As a matter of fact, we did two examples to solve a circuit that has a dependent sources, dependent current source or a dependent voltage source using the node voltage method. So let's see if we can go to the mesh current method. Okay, so let's first try to understand what a mesh is. Okay, so when you have nodes, you apply node voltage method, which is simply an application of Kirchhoff's current law at each node. When you have mesh, okay, you apply mesh current method, which is simply application of Kirchhoff's voltage law around a mesh. So in order to apply that, we first have to define what a mesh is. Okay, mesh is a subset of loop. Okay, subset of a loop. So mesh is a loop that does not contain any other loop inside it. Okay, so let me show that on this circuit here. Okay, if you look at this circuit here, you can define any number of mesh, any number of loops. So for example, that is a loop. Okay, it's a loop because that guy is a loop because it begins and ends at the same point. It begins at that node and leads back to the exact same node. Hence, it's a loop. It's a closed path. Okay, but it is not a mesh. It's not a mesh because there are other loops inside it. There's another loop inside that loop. So that makes it not a mesh. So there's another loop. Here's another loop. So if there are other loops contained within that loop, then it's not a mesh. Let me draw a mesh here. This guy is a mesh because it does not contain any other loop in it. So a loop which contains no other loops in it, that's called a mesh. Okay, so that's the definition of a mesh. So let's go back. So mesh current method is another way to create the necessary equations. Okay, it's another way to create a necessary equations. This is an alternative to the node voltage method. Okay, so this is a variation of, like I mentioned, the KVL, application of KVL. Okay, let's define a mesh. Okay, now there are three loops in this circuit which meet the definition of mesh that I just mentioned. Okay, there's one loop here which is a mesh. There's another loop here which is also a mesh. There's a third loop here which is also a mesh. Okay, so there are three meshes here that meet the definition of mesh. Three loops that meet the definition of mesh. Okay, so let's go ahead and see how we can apply the mesh current method. Okay, let me go further down. Okay, let me go further down up to this point. Okay, and add a page there. I'm sorry, give me 1 second. I see. This does not want to copy because there seems to be some. Okay, let's try it now. There you go. Okay. All right. Sorry about that. So here is an example of how to apply mesh current method. Okay. Step one is to identify the independent meshes. Identify all the meshes that are present in this circuit. Okay. And like I mentioned earlier, this is one mesh. Okay, that's one mesh. There's another one. There's this guy. That's a mesh. And there's a third mesh, which is this guy. Okay. There are three meshes here. Step 2 would be set up mesh currents. Meaning I'm going to define this current a current I1 as the current flowing in mesh 1. Similarly, I will call a current I2 that's I1. Let me call a current I2 this guy, a reference current I2. Okay, and I'm also going to write another reference, a third reference current I3, like so. Okay, in order to follow the convention, I assume that the reference current direction is clockwise. I assume a clockwise direction for the currents. Okay, set up reference mesh currents for each mesh. Now, the third step is to write KVL equations for each mesh. So let me show you what I mean. So there are three meshes here, mesh 1. Okay, there's a mesh 2 shown in blue, and there's a mesh 3 shown in green. Okay, mesh 1, 2, and 3 shown in purple, blue, and green. Okay, so what I'm going to do here is to, as a part of step 3, I'm going to write KVL around mesh 1, which is the purple mesh. So in order to follow the convention, we start at the lower left corner and follow a clockwise path, and write the voltage drop across each of the elements. Okay, so that's the idea of KVL. So to begin with, I have negative 40 volts. Okay, negative 40 volts for that voltage source, followed by plus minus 2 ohms into I1. That's the current flowing through the 2 ohm resistance. Then I see the 8 ohm vertical resistance, okay, that is shared between the blue path and the pink path. Okay, that's this guy I'm talking about. This resistance right here, the 8 ohm resistance that is carrying a current of I1 going south and I2 going north. Okay, so there are two mesh currents flowing through the 8 ohm resistance. So what I do is to take the 8 ohm resistance and multiply that by I1 minus I2. All of that should equal 0. Okay, so that's the idea of setting up KVL for mesh 1. Okay, let me try to write the equation for the second one and see if it becomes clear. Okay, KVL around mesh 2, which is the one in the middle. Okay, let's zoom in on it and see what's going on. Okay, That's the mesh I'm interested in, and that's the mesh I want to, um, for which I want to set up the KVL. So I start at the lower left corner, which is the 8 ohm resistance, right? 8 ohm resistance. Follow a clockwise pattern, okay? Follow a clockwise pattern like so. Right? I follow a clockwise path. The first resistance or the first circuit element that I encounter is the 8 ohm resistance. See, when I encounter the 8 ohm resistance, I see a current of I2 going up and I1 going down. I2 is going up and I1 is going down. Therefore, here is how I set up the KVL equation for that. 8 ohm resistance into I2 minus I1, that's the total current flowing in the 8 ohm resistance, plus the second resistance that I see in the path is the 6 ohm resistance. So 6 ohm resistance is carrying a current of I2 in the clockwise direction. Therefore, this is 6 ohms into I2 plus. Now I come to the last element of the path of the blue loop, okay, which is the 6 ohm resistance, vertical 6 ohm resistance, okay. If you think about it, there is one current I2 flowing in this direction, and there's another current I3, the green current flowing up. So the net current that is carried by the 6 ohm resistance is actually I2 minus I3. Okay, it's I2 minus I3. So I set up a, a third term here, 6 ohms into I2 minus I3. All of that equals to 0. Okay, all of that equals to 0 is the idea of KVL around mesh 2. Okay, let's see if I can do the exact same thing for mesh 3 KVL around mesh number 3. Okay, if I do that, I'm looking at the green mesh over here. And as always, I like to start at the lower left corner. Okay, start at the lower left corner and follow a clockwise path. The first circuit element that we see is this 6 ohm resistance here. This 6 ohm resistance is seeing a current of I3 that is along the reference direction, and I2 that is opposite to the reference direction. So the current here is going to be I3 minus I2. Okay, so if I were to draw the, if I were to write the voltage drop there, it will be 6 ohms into I3, which is along the reference direction for that loop, minus I2, which is opposite to the reference direction. Similarly, after the 6 ohm resistance, I follow along the path to find a 4 ohm resistance, which is simply carrying a current of I3. Okay, therefore I have I3 times 4 ohms. I3 times 4 ohms. Okay, plus the next element I encounter is this 20 volts voltage source, and the reference direction current is along the voltage drop from plus to minus. Therefore, I'm going to call this guy as a positive, okay? Because the voltage drop is along the direction of the current, I'm going to incorporate a plus 20. All of that equals to 0, okay? So this is how I set up mesh current method. Okay, I set up mesh current method. Let me see if I can copy these again. I set up the mesh current method like so. So I have three equations here. There's one equation right there. There's another equation and a third equation. Okay, so it's a matter of solving these three equations together. Okay, let's see if I can write these three equations in a format that is convenient for me. Everybody with me so far? Okay, so what I'm going to do is to look at each of these equations. Okay, let's look at the first equation to begin with, equation 1, and I'm going to write it in terms of the independent variables. I1, if you look at I1 is 2 ohms and 8 ohms term. So there's a 10 ohms over there. Plus, if I add up all the terms that contain I2, I'm going to be left with minus 8 ohms for I2 plus I3. There's no I3 term in here. So I'm going to simply write it as 0 ohms. Okay, all of that equals to 40 volts. Okay, that guy. That 40 volts taken to the other side is going to be 40 volts. Okay, so that's equation 1. I'm going to rearrange equation number 2 in terms of the independent variables. So look at the terms that are containing I1. There is a negative 8 ohms term, and that's about it. So I'm going to write negative 8 ohms times I1 plus, let's look at the terms that contain I2. Okay, there is I2 is in a bunch of different places. Okay, so there is 8, there is 6, there's another 6. If I add them up, I'm going to have 20 ohms times I2 plus, let's look at the I3 term. What's seen for the I3 term? I3 term has a negative 6 ohms, and that's about it. Okay, so negative 6 ohms times I3, all of that should equal 0. Okay, so that's equation number 2. Let's rearrange equation number 3 in terms of the independent variables. Okay, let's see if I can write the equation number 3. Let's look for I1. There is no I1 term in equation number 3. So I1 times 0 ohms plus, let's look at the I2 terms. Okay, there is a negative 6 ohms term in there. So negative 6 ohms terms I2 plus, let's aggregate the I3 terms. I3 has 4 and 6. So there's going to be a 10 ohms I3. All of that is 20 volts. Take it to the other side, becomes negative 20 volts. Okay, now you have three equations. All of these are in a format that is very convenient to plug into MATLAB. Okay, these are the unknowns I1, I2, I3, and the coefficients are 10 ohms, negative 8 ohms, 0, negative, okay, negative 8, 20, and negative 6, followed by 0, negative 6, and 10. Okay, so these are the coefficients, and then constants are 40, 0, and negative 20. Okay, there is A, there is B, and there is C over here. We should be able to plug them in to MATLAB. Okay, let's go back and see what the example problem did earlier. Let me go back carefully. Okay, that's exactly what has been done. Um, Setting up the equations in MATLAB. Okay, 40, 0, negative 20, IA, IB, and IC, which I named as I1, I2, and I3. And then the coefficients 10, negative 8, 0, negative 8, 20, negative 6, 0, negative 6, 10. Okay, the exact same process that we discussed. When you plug it into MATLAB using these simple lines of code, okay, A is the matrix that you plug in. B is also the matrix that you plug in for this guy, okay? And then C is the unknown variable that you want to find out. C is A over B. MATLAB will throw out the values for IA, IB, and IC to be 5.6 amperes, 2 amperes, and negative 0.8 amperes. Okay, so that's how you would solve. Earlier, you would set up equations exactly similar to this, but using KCL in the node voltage method. But KVL, you use mesh current method. Okay, questions, please. Questions so far? Okay, let's see if you can. I want to give you a problem to work on. Let's see if I can go back here. Questions? Okay, so now a special case for a mesh current is when the branch contains a current source. Okay, when one of these branches contains a current source and you're setting up a mesh current, okay, if you're setting up a mesh current like this, okay, I don't know, there's one mesh, a second mesh, a third mesh, a fourth mesh. Okay, there are 4 meshes, so I'm going to call this as I4. Okay, in I4, when you're writing the mesh equation, why don't I do this? I'll get you started here. I'll get you started and write expressions for 2 of the mesh equations, and then have you do the rest. Okay. So one thing you want to understand really is when you're setting up the mesh equation for this current and call this as I4, okay, I4, one of the equations that is going to come away directly is I4 is negative 4 amperes, okay, because what's I4? I4 is a variable that represents a current flowing in this direction, okay, I4. But that's exactly the opposite of this 4 amperes. And that's what I express as an equation here, I4. So this is an additional equation that you get from the constraint equation of the independent current source here. So when one of the branches contains a current source, you get a bonus equation. Okay, you get a free or bonus equation. All right, so we can set up any number of equations here, 4 equations and 2 additional equations. Okay, let's see. So it's a free or bonus equation, also called a constraint equation. So let's go back. Okay, so this is a special case for a mesh current. This happens when one of the branch contains a current source. When one of the branch contains a current source, like I showed you earlier, it leads to an additional free bonus equation. And the concept that we are not going to look at in this class is the idea of a super mesh. If this branch current is between two different meshes, if this is shared between two different meshes, then we would usually form a super mesh. We don't talk about that in this class. Okay, but when the branch current is not between two meshes on the outside of the mesh loop, then the current constrains the mesh current. Okay, this current, okay, constrains the mesh current. That's simply saying there's a free or bonus equation. Okay, this mesh versus branch current constraint is due to the requirement of charge conservation. The current must be continuous for both the branch and the mesh current at that point in the circuit. Okay, so let's try to see if we can solve this guy. Let's try to see if we can set up equations for this guy. Okay, I'm going to copy this. Okay, of course, the solution is available right here. I might as well, do some hand waving and point you to the equations right here in thin air and claim that I talked about this. I don't want to do that. I really want to work on these problems from ground up, just so you're much more comfortable setting up these equations on a blank sheet of paper. Okay, as I talk to my students and as I read the feedback, okay, I get a sense that an additional an additional clarity is added when I start working on the problems from a blank page rather than just showing them already worked out on an example PowerPoint slide. And that's the reason I tend to work out everything on paper, even though it's available on already solved for me. I don't like to do that. I like to work on this from ground up, just so it adds an additional layer of clarity. For example, if I give you this problem and ask you to solve using mesh current method, okay, where do you begin? Where do you begin? It's easy for me to just say, well, here is the equation one, here is the equation two, here is the equation three. But I want to simulate in some sense how you would go about solving the problem if you were given this. Well, the first thing you would do is to identify what your step number one is. Okay, what's step number one? Step number one is to look at all the meshes, identify all the meshes. Okay, the first mesh is this guy. So I can get one equation from there. Let's see if there's another mesh. There's a second mesh over here. That's this guy. Okay, it's a definition of, it's a loop that meets my specification of what I call as a mesh. Okay, then there's a third one. It is this guy. It begins and ends at the same point, but it does not have any other loop associated inside. And there's a third one. Let's look at this guy. Four meshes. Okay, there are four meshes here. Mesh one, mesh two, mesh three, and mesh four. Okay, so that's step one. I identified all the meshes. The second step would be set up a reference mesh currents. Okay, that's pretty straightforward. Okay, each mesh has one current, so I'm going to call this current I1. Okay, I'm going to call this current as I2. Okay, and I'm going to call the third current in the third mesh as I3, and this guy as I4. Let me find a place where I can I4. Okay, that's I4. Now, if I look at this circuit that looks like this, what would be my next step? Step number 3 would be to set up equations by applying KVL. So using KVL around each of the 4 loops. Okay, I have 4 loops. Therefore, I set up 4 equations. Okay, so this is how I would go about. Okay, KVL around mesh number 1. Okay, so let me rewrite this to be mesh. Questions, please. Questions so far. Okay, then I would do KVL around mesh 2. So that's the one shown in purple, KVL around mesh number 2. Okay, then I write KVL around mesh number 3 and 4. Okay, let's see if I can. Okay, this guy is blue. Okay, KVL around mesh number 3. Okay, that's the one shown in blue. And then there's KVL around mesh number 4. It turns out that 4 mesh equations are not enough here. Okay, if you look at the unknowns, there is I1, I2, I3, and I4, 4 unknowns, and not just that. There is another guy. Don't forget this I5. Okay, don't forget this I5. That guy. Okay, so it seems there are 5 unknowns. Okay, there are 5 unknowns. In order to solve those 5 unknowns, I would need 5 equations. Okay, I would need 5 equations. So let me see if I can set up equations. Okay, what I'm going to do is to have you, okay, I will have you work on KVL around mesh 1, KVL around mesh 2, KVL around mesh 3, and KVL around mesh 4, while I set up the constraint equation. Okay, let me see if I can show you the constraint equation. How can I? Okay. also solve using mesh current method. I'm going to sneak the constraint equation right up here, okay? This guy. The constraint equation says that I2 plus I2 minus I5 equals to 0, okay? If you think about it, this current, okay? The current that is flowing through the 5 ohm resistance, okay? The current that is flowing through the 5 ohm resistance, that's I2. This guy is I2, right? And then the same current, when you express it as a variable flowing in the opposite direction, it's I5. So my point is, I2 is exactly same as negative I5. Okay, is everybody with me? That's like saying I owe you $5 million. Okay, is the exact same as saying, is identical in all respects as saying you owe me negative $5 million. Okay, you owe me negative $5 million. Okay, so that's exactly what is happening here. This 5 ohm resistance is carrying a current, the pink current of I2 in the clockwise direction from left to right, from west to east. The eastbound current I2 is exactly identical and opposite to the westbound current I5. Okay, I5. That's exactly the equation that I use, the fifth equation. Equation number 5. Okay, so I have 4 equations that will come about when I set up the KVL around each of these meshes. And then a 5th equation I can get from here. Okay, and also don't forget that I4 is negative 4 amperes. Okay, if you look at this I4, I mentioned earlier, I4 is the current that is going south. It is exactly opposite to the 4 amperes current that's going up. Okay, opposite means negative, so therefore in negative 4 amperes. All right, so what I will do is to fill in one of these equations for you. Which one would you like for me to fill in?
Could you do the one for the blue mesh?
Blue mesh.
Yes.
This guy, right?
Yes.
Okay. We start at the lower left corner and follow a clockwise path. Okay. When I begin at the lower left corner, okay, there is one current, and I see the 50 ohm resistance there. Okay, I see a 50 ohm resistance. One current I3 is going up. One current I2 is going down. Right? So what I'm going to do, I'm going to write this 50 ohms. I wanted to use this color, right? So 50 ohm resistance. The current flowing in there is I3 is going in the clockwise direction, or I3 is going in the direction of my reference, and I2 is going opposite to the reference direction for me. Okay, plus, then I encounter this guy. Okay, so I'm following along in a clockwise path. The first one is the 50 ohm resistance. Then I encounter the dependent voltage source. Okay, it's a dependent voltage source. So all I have to do here is to notice that this is negative 10 I5. Okay, plus it's a voltage source. I don't have to apply the IR formula. All I have to do is negative 10 times I5 is the voltage dropped in that guy. Okay, plus let's do the other resistance, the 100 ohms resistance. There is one current I3 flowing down, and then there is one current I4 going up. There are two currents, right? So I3 minus I4 times 100 ohms, all of that should equal 0. Okay, so if I were to clean this equation up, I'd get, okay, equation 3, right? Equation number 3. If I were to write in terms of the independent uh, design variables, there is no I1 term, I1 into 0, plus I2 term has negative 50, I2 terms negative 50, okay? Plus, let's see what's included in I3. There's a positive 50 and there is a 100, okay? There's a positive 50 for I3 and there's a 100 ohms over there, okay? So I3 times 150 plus what's included for I4? I4 has a negative 100, okay, right? So I4 has a negative 100. So that's what I'm going to include. I4 times negative 100 plus, let me look at I delta, I5, okay? I5, there's a negative 10 term over there, okay? Negative 10, all of that equals 0, okay? That would be my equation for mesh 3. Okay? Let me go back there. Questions, please. Questions so far. All right. Why don't you take about 10 minutes to set up the rest of the equations? KVL around mesh 1, around mesh 2, and around mesh 4. Okay. So you need, there are 5 unknowns here. If I go back to the equation eventually, the equation has 5 unknowns, I1, I2, I3, I4, and I5. I5. Okay. Fortunately, I gave you this equation number 5. Equation number 5 said I2 equals to negative I5 or I2 plus I5. I2 times 1 plus I5 times 1 equals to 0. Because I2 equals to negative I5, the rest is all 0. I3 times 0 plus I4 times 0 plus I1 times 0. So I have an equation number 5. So you want to write equation 4, 2, 1. So let's see if you can take exactly 10 minutes, okay, to set up this KVL around mesh 1, KVL around mesh 2, and mesh 4. Okay, let me, give me 1 second. All right, let's solve this problem. Let's see, who can help me set up the equation number 1? Any volunteers to do that? It's a very simple equation.
So for equation number 1, I went around mesh 1, which is has current I1, and so that I got negative 50 volts plus 40 ohms times I1 equals 0.
Plus I1 equals to 0. Very close. You may have forgotten another component in there, the I2 component.
Yes. Okay. Minus I2. That's correct.
Minus I2. Perfect. Perfect.
Yes.
That's correct. I1 minus I2 equals to 0. For some reason, my Apple Pencil does not want to respond. Let's see if it's any better now. There you go. Okay. So what you have is minus 50 volts plus I1 minus I2 times 40 ohms. All of that equals to 0, right? So this is equation 1. Let's see, how about equation 2?
For equation 2, then it would be negative 40 times I1 minus I2.
Sure,
And then
I2 minus I1 times
okay.
40 ohms. That's exactly what you did. I just rearranged I1 and I2. I2 minus I1 times 40. Yes,
Okay.
then?
Okay. So then with that, then it would be minus 5 times I phi minus I2.
Minus 5 times I phi minus I2. Sure, yeah. What we want to see is that there's only one current flowing in here. Okay.
Okay.
So I phi.
I can't see your screen.
We can't.
No, I can't.
My bad. How did that happen? Share content screen. And how long has it been like this?
It probably went off about 5 minutes into working the problem.
My bad, my bad. So it's the auto lock screen. So my bad. Sorry about that. So I'm going to set up the equation for mesh 2 and then we'll see why that's the case. Okay, 5 ohms, okay, is the resistance times I2. That's all. I'm not going to incorporate I phi or I phi plus, and I'll come back to talking about why that is the case. Okay, plus, what did you have for the third term?
Well, do you want me to tell you what I had, or because I know the first term was flipped, so I was flipping them. What I have is plus 50 times
Okay.
I2 minus I3.
Yes, that's it. I2
Okay.
minus I3. All of that equals to 0. Okay, so let me show you why I have these terms as flipped, or in other words, why they appear flipped to you. Okay, I'm writing the mesh equation for the second mesh, okay, beginning with the lower left corner. When I begin with lower left corner and I want to go in the clockwise direction, I2, I want to go up, I2 is in the positive direction, is along the clockwise direction. Okay, so in other words, I'm going clockwise. How is I2 going? I2 is also going clockwise. They're aligned, so I make it positive. Okay, similarly, I'm going up. How about I1? I1 is going down. So my reference direction is up, while this current I1 is going down. Therefore, I incorporate a negative sign. Okay, therefore, I incorporate a negative sign. And that's the reason why this I1 right here is negative, because it's opposite to my reference direction. Okay, that's one point. Let's look at another, let's see another thing. It would appear that there are two currents flowing in here. There is one current I2 going in this direction, and you almost have a very strong temptation to want to put another I5, like so, right? But that's really not the case. The reason is, if there was another mesh like so, and I5 was going like this, then there would be a different current, okay? But what you want to notice here is I5, okay? There's only one current there's only one current in this branch. There can only be one source for this current. There can only be one current, I2, which is exactly the same as a variable I5. Okay, this is not an independent current. It's just a different way of looking at I2. Okay, there is no condition that sets up an independent current I5. Okay, does that make sense?
Yes, it does. And so that means that that's why I2 equal to I5 is our constraint equation.
Yes, I2
Okay.
equals to negative I5 is our constraint equation. Okay, and then talking about this guy, the third one, okay, the third one is that I2 is going south, and which is aligned with my reference direction of clockwise, and I3 is going opposite to my reference direction. It's going opposite to my reference direction, therefore negative I3, okay, times 50. So what you have is perfect, okay? So that's KVL around mesh 2. Do you also want to help us with KVL around mesh 3 or mesh 4? We did mesh 3, right? Let's do mesh 4.
Okay, I remember the equation you gave us for mesh 4 was I4 equals to negative 4 amps. And so I was a little confused with mesh 4 because I didn't quite know how to set it up.
Yeah, yeah.
So I know it would be, well, if we were starting from the bottom left corner,
Okay.
and that would be 100, and then our reference current goes down or in the clockwise direction. That's
So reference current goes up.
goes up, right? Okay, so then our reference current goes up. So that means the current would be positive going up. So it would be
Thank you.
100 times I4,
Yes.
and then I'm not sure. Is it minus 4 equals 0? Or I just wasn't sure how to put in the 4 amps into the equation.
Yeah, it's the voltage drop that we take into account. The voltage drop across this guy is 100 ohms times times the okay. It's I4 times let's see, 100 ohms is let's see, I4 mesh 1 is I1 times 0, I2 times 0, I4 equals to minus 400. Okay, and then what's the voltage dropped across this guy? Okay, that's equals to the voltage dropped across this guy. So voltage dropped across this guy is 100 times I4. I4 is negative. So in other words, this guy, okay, I'm going to have to make a little diversion here and make it seem like, let me call this V4 amperes, okay? So this voltage plus voltage across 4 amperes should equal 0. Or in other words, the argument that I'm going to make is that I4, okay, the voltage applied across, now I plug in the value of I4 equals to, I4 equals to negative 4 amperes, okay? And I plug in the value of I4 equals to negative 4 amperes, okay? What I see is this guy Okay, I4 equals to -4. Okay, so that's the constraint equation that is coming for the um, mesh over there. Okay, so I can directly plug in the equation that I gave here, I4 equals to -4 amperes. But if you were to set up, okay, if you were to set up the KVL around this loop, the voltage that is dropped around this 100 ohms resistance should equal the voltage that is dropped across the 4 ampere resistance. Okay, so for the mesh 4, you simply use the constraint equation that we saw. Okay, I4 would be -4 amperes. I4 is -4 amperes is the constraint equation that we got. Okay. So let's do, for mesh 4, I'm going to use the constraint equation. Which says I4 equals to -4 amperes. Okay, so this is equation 1, equation 2, equation 3, and equation 4. Okay, 4 equations, and I have, if you were to set up the KVL, you would have to include I100 times I4 minus I3. That will be the voltage drop across that guy. Okay, now let's see. So I have 1, 2, 3, 4, and 5 equations. 1, 2, 3, 4, and where's the 5th equation? My 5th equation is right here. Okay, that's my equation number 5. So once I put all of these 5 equations together, I should be able to let me see if I can copy these equations separately. Copy this. Okay, I'm going to paste them over here. And so I have 5 equations here. 1, 2, 3, 4. And the 5th one is just this guy. Okay, I5 equals to negative I2. That's my constraint equation. Okay, from the independent source. So I can rearrange this in the form shown above. Let me go back. So I can rearrange the 4 equations to appear like this. Okay, and then I have the 5th equation, I2 plus I5 equals to 0. And therefore, 5 unknowns, 5 equations I should be able to solve for the values for I1, I2, I3, I4, and I5. Okay, using MATLAB. Questions, please. Questions so far?
I have a question.
Yes.
For the I4 equal to -4, if I were setting up a matrix in my calculator, where I have a, so this is a 5x6 matrix, would I just put in for I4 like across the row 0, 0, 0, and then basically plug in -4 in my matrix for the I4 variable? I don't know if that
Yes,
makes
you do that.
sense. Okay.
Yeah. Yeah.
Okay.
It's like I1 times 0 plus I2 times 0 plus I3 times 0 plus I4 times 1 plus I5 times 0 equals to -4. So however you plug that into your calculator, you can do that. Okay. Other questions, please. So you plug in 0, 0, 0, 1, 0, and -4. As a matter of fact, let's see if I can, I think it's up right here. Okay. So the matrix that you have is 1, 2, 3, 4, 5, 6. Six columns and 5 rows, 5 by 6. Okay. And if you're talking about this mesh equation, it's 0, 0, 0, 1, and 0, and -4. All right. Questions, please. What other questions do you have? All right. So let's go back and catch up with our syllabus. Let's see, syllabus. Okay. Today is the 21st. All right. Today is the 21st. Mesh analysis. Tomorrow, we're supposed to be doing mesh analysis with dependent sources and special cases. So what we'll do is we'll do some more examples for node voltage method and mesh current method tomorrow. Okay, and the day after, that's the Thursday. So on Thursday, we'll come back and look at source transformations. Okay, we'll talk about source transformations on Thursday. But tomorrow, we'll come back and look at some example problems for mesh analysis and nodal analysis. Okay. Any last questions? Okay, we'll stop here. I'll see you folks tomorrow.